Hello, everyone. I'm very glad to see that you joined our InfoShare. It is the last one that will take place this year, but of course, next year we will have more. This one is on community tools, quantum tools in our community that were community built. And we are conducting this InfoShare as part of Work Package 6, Task 1. And the tools that we will see and that we will be shown and discuss are solutions around KMS systems for quantum key distribution, but also network programmability in the context of QKD. We will have three speakers or three presentations, I should say, and four speakers altogether. There will be a presentation by the University of the Basque Country, and there will be actually two presentations from the University of the Basque Country, and a third presentation from SURF, the NREN of the Netherlands. We will start with the presentations. Usually, we should have time for one or two questions after each presentation. And if that is not enough time and there will be more questions, please put them in the chat or ask them later at our question and answer session in the end. So there should be ample time for all the questions that you may have. I think we can go ahead now and start with the first presentation. It's called On the Road to Scalable Quantum Communications, the Benefits of Network Programmability. And it will be presented by Asier, Atutxa, Imatz, and David Franco from EHU.
Susanne said, we are Asier, Atutxa, and David Franco, participants in GÉANT's GN5-2 WordPack 6-1. And this presentation lays on the road to scalable quantum communications, the benefits of network programmability. Okay, this is the agenda. In this InfoShare, we will present the integration of quantum communications in traditional networks, with a special emphasis on the challenges. Then we will identify the benefits of network programmability, first addressing the control plane and then the data plane. And last but not least, we will end the presentation with some conclusions. Quantum communications and networks based on technologies such as quantum key distribution are exposed to similar challenges as traditional networks, mostly due to the complexity of the networks, which can have different topologies and security domains. Firstly, just as in classical networks, the management of the network and the management of the keys is a great challenge to solve. And it is not always feasible to base on a statical configuration. The scalability is another factor, as the implementation of quantum-aware nodes in the entire network is not economically and logistically feasible. And finally, the multi-technological nature of current and next-generation networks, such as 5G, hinders the deployment of quantum communications. In fact, it is not the same to secure the interfaces of the 5G RAN or non-3GPP access networks, or even the service-based core networks. Therefore, it's important to note that classical networking concepts can be applied to solve several of these issues, such as distributed protocols or centralized orchestration that we will be addressing in this presentation. In general, making quantum communications as accessible as possible is beneficial, taking into account the current constraints of the technology, such as range, trust, and cost. The integration of quantum communications, or for the integration of quantum communications, the ideal scenario is a fully quantum-aware network with all nodes that have, with all of those nodes having QKD equipment and capabilities. However, this is usually not the case, and some nodes do not have QKD equipment. In this case, nodes can be enhanced, for example, using PQC mechanisms, so they are capable of providing, let's say, quantum security. And therefore, in these heterogeneous scenarios, the establishment of end-to-end security channels is not straightforward. The use of trusted relays, for example, enables the extension of keys from one end to another. However, how do we establish the path from end to end? For linear topologies, for example, it's easy, it's more straightforward. But for mesh topologies, a path computing algorithm or something similar is needed or must be implemented. Therefore, in this presentation, we gather several techniques from network programmability that can help in the integration of quantum communications. We divide the presentation in two parts, one dedicated for the control plane and another one for the data plane programmability. We will explore first the current trends related to the topic of control plane programmability and QKD. Control plane programmability plays a crucial role in QKD-based quantum networks. The reason for this is mainly that ETSI has released various standards that are based on the SDN approach to control QKD nodes. For example, the ETSI 015 or the ETSI 018. Then Teraflow SDN is a well-known SDN controller created in the context of a European project, and it is compliant with most of the CS standards. The following picture, for example, depicts the architecture of Teraflow SDN. It has several components dedicated to, for example, controlling IP routing. In addition, Teraflow SDN provides northbound and southbound interfaces to communicate with upper layers and devices in the data plane, respectively. It also defines interfaces for communicating with other HCNFV entities, such as the management orchestration components. It is true that not all the interfaces mentioned above are yet implemented in Teraflow SDN. However, it provides a flexible programming interface to implement custom APIs. For instance, participants of the 6G OpenSecKeys project have implemented XC-QKD interfaces for the integration of QKD nodes into Teraflow SDN framework. The goal in this project is to develop a let's say QKD SDN controller that can manage QKD-related resources from a centralized entity that is the Teraflow SDN controller. Following with the centralized approach, Toshiba also developed its own SDN controller to manage QKD resources, as shown in this picture. They use netconf plus the HC015 to implement the southbound interface. In this case, they went further and they also use QKD keys to encrypt the communication in the southbound interface itself. This means using QKD to secure QKD management, which is an interesting approach. Also, MACQC is another example of centralized SDN controller for QKD. MACQC is a QKD network formed by several QKD nodes that expose the HC015 interface to a centralized controller that is in charge of their configuration. The network provides relaying capabilities, implementing QKD relay nodes, and exposing different interfaces to relay QKD keys. The key relaying process is, in this case, is static. Two nodes are set as end nodes, and the intermediate node acts as the relay for both ends. This means that key retrieval is only allowed at the end nodes, as it is depicted in this picture. Then our team at the EHU, in the context of the GÉANT 2 project, developed a QKD framework focused on dynamically establishing key relay paths. The quantum security controller, or QSEC, is an SDN controller that implements the HC015 interface and manage the establishment of QKD key relay paths from a centralized perspective. It interacts with QKD nodes through a novel entity called virtual KMS to push the required configuration in order to set the key relay paths. This approach is fully compliant with ETSI standards such as O15 and O20 for key relaying, and key retrieval is allowed from every node in the network. This means secure key establishment is possible from any to any node of the network that has a QKD node. The solution has already been implemented in simulation environment, and it is planned to be deployed in real equipment as part of the SmartNets for which is an experimentation facility owned by EHU and which also has a direct or which is directly connected to the GP4L, for example. And once we have reviewed the current trends in the context of control-plane programmability and QKD, let's see which are, from our perspective, the potential research lines that can help in the evolution of QKD and quantum networks. The EHU team we are also carrying out a research activity to improve the relaying of QKD keys. In our previous work that I have already mentioned, we relay QKD keys between nodes that have QKD equipment. And the goal now is to use PQC to extend the quantum security to those nodes that do not have QKD equipment. This work focuses on adapting QKD network to real scenarios in which QKD and non-QKD or classical nodes need to coexist. For this purpose, we define 4 security levels that represent the different combinations of QKD and classical nodes. The 2 pictures at the top of the slide represent the levels 1 and 2, which are the same as in our previous work. And level 3 at the bottom of the slide represents the key relay process between a classical node and a quantum node. And level 4 does the same for 2 classical nodes. In these levels, PQC is used to either create or cipher a quantum safe key, as it is represented in the pictures at the bottom. This is an ongoing work, but the most relevant results are publicly available, and in the following presentation, more details about this will be explained. Another potential research topic that is expected to be relevant is the orchestration of IP and QKD resources. If you want quantum networks to be real, it is of utmost importance to combine IP and QKD domains or resources so they can be managed from a single point or entity. This means coordinating both the configuration of quantum resources to generate QKD keys and the allocation of IP or networking resources to provide connectivity to the relay path. ETSI, for this purpose, for example, ETSI defines the concept of management and orchestration, which could be used at this point. Besides, the ETSI 018, in the context of QKD, defines the northbound interface to interact with this element, which opens the door or paves the way for the integration of QKD with orchestration platforms. The picture depicted in this slide shows a tentative approach for this integration. We can see IP and QKD related northbound and southbound interfaces, as well as the role of SDN controllers in this architecture. Okay, so now I will give the floor, literally, give the floor to my colleague Asier. Okay, so now we will switch to data plane programmability. And here, the current trends can be gathered into 2 main groups. First, the efforts towards the coexistence of quantum and classical channels using optical solutions for the multiplexing of both signals. And second, the multi-layer integration of the QKD generated keys in the different cryptographic protocols. So regarding the coexistence of channels, the integration of both channels vastly benefits the scalability and deployment of quantum communications, as it removes the necessity of dedicated dark fibers for the quantum channel. For this purpose, the most common approach in the literature is the copropagation of both channels through the same fiber strands using wavelength division multiplexing equipment or WDM. And these passive systems can be used for manipulation of the quantum channel, while attenuators and amplifiers can be used to adapt the power of the classical channel and the impact of the Raman scattering. And in this context, several works have started to study the programmability of the optical WDM equipment, orchestrating and automating the configuration of transmission parameters, such as the wavelength of each subchannel or the separation between both channels. So thanks to this, it is possible to dynamically allocate the fibers of a network, switching operations from single fiber bidirectional to dual fiber operations, for example, among other alternatives. Therefore, the use of fibers in transport networks can be dynamically set depending on the necessities of the scenario. And this can be done by leveraging programmable devices. On the other hand, the most part of the efforts regarding QKD in the data plane have been put into the encryption systems. And these can be also sorted into three main categories, depending on the layer in which they are applied. So first of all, returning to optical networks, physical layer encryption through WDM equipment is a typical use in transport networks. However, since the advent of QKD technology, commercial WDM systems have incorporated the support for encryption using QKD-generated keys. So these systems implement now standards like ETSI QKD 014, and so can query the KMS systems and retrieve keys, which are then applied in the encryption of line rate at, for example, 400 gigs. And here, as you can see in the figure, one of our previous works regarding this matter. And in higher levels, there have been several works in the scientific and industrial world towards the implementation of efficient symmetric encryption with QKD keys. And here, following the current trend, heterogeneous networks with several different security domains and protocols in each interface can make use of these approaches. For example, the specification of the 5G architecture defines several security protocols depending on the network segment. So this creates a diverse and complex security environment. And in this regard, the implementation of link, network, and transport layer encryption and authentication protocols in the data plane of programmable networks is a strong starting point, which has been done recently with protocol suites like MACsec or IPsec or even TLS. For instance, there have already been works that apply QKD keys in the authentication of IPsec in the EK protocol, as well as in the tunnel and security association establishment of ESP. The implementation of these solutions into programmable devices provides more flexibility to the network. And in fact, similar to previously presented optical transport networks, being able to dynamically adjust and process the packets depending on their requirements, that improves the performance and flexibility of networks. Finally, current efforts in the research community are also focused on the quantum internet. And specifically here, researchers are working on the transmission of quantum information encoded in qubits rather than in classical bits, which means that the end-to-end transmission and the networking nodes must adapt to the parsing and the processing of this data. Here, innovative proposals have also been presented, such as QIP by SARF, which are here in the code. This work by SARF proposes a framework that provides a way to specify how quantum and classical information are processed in the quantum network in a quantum network node, similar to how P4 switches describe packet processing pipelines in classical programmable switches. So to conclude, some potential research lines could include the offloading of key relay procedure to the data plane. Could also work on the integration of post-quantum cryptography into programmable data planes, or on the integration of encryption mechanisms into P4 switches and similar systems. And finally, we would like to highlight which, based on our experience, are the main benefits of network programmability in quantum networks. First, the programmability and centralized approach of SDN provides real-time rerouting, which is crucial to keep the key relaying service available in the event of link or node failures. Also, network probability is key in providing dynamic configuration of key relay paths, which is necessary in real scenarios where topologies are always changing. Third, network probability allows for the easy implementation of interfaces to interact with network orchestration entities that can manage both IP and QKD resources. And finally, programmable data planes open the door to offloading quantum-related tasks such as key relaying, ciphering, or cube prototyping of quantum protocols, which could enhance and accelerate some functions. So this was all. Thank you for your attention.
Okay, thank you very much. Very, very interesting. Are there any questions? I see Wojciech. Please go ahead.
Yeah, thank you for the great talk. It's interesting to actually see uh, programmability show up. As you notice, I am very interested in that topic. I have one question based on my personal experience, which was that whilst P4 is a great language, I found that, I mean, in hindsight, perhaps quantum needs its own domain-specific language. Admittedly, creating your own domain-specific language is enormous work because then you have to write a compiler, you have to have hardware targets, etc. But do you think it's an interesting avenue to pursue?
I mean, for sure, it could be interesting. You mean like a similar approach of P4, but for quantum networks, right? I
Yeah,
believe.
because P4 is packet. I mean, it's very focused on packets, but even though you can adapt it because of its architecture flexibility to other approaches, I was just wondering if it's better to have maybe, it's a domain specific language, so why not have something that's very specific for the domain of quantum or maybe QKD?
Yes. Could be a pursuit, but I believe that requires like an enormous amount of effort, and probably you would have to involve. I know if manufacturers or at least like big entities, but for sure it could be an interesting topic for sure. Yes, I believe that it will be done at some point. I don't know if it's too soon or if it's already been done in some innovation and development team, but for sure it will be done at some point, I believe, yes.
Right, thank you.
Okay, thank you. Are there any other questions? I have one question. The centralized controller that you mentioned from QSEC, is this a tool that would maybe also be available as a open source tool somewhere down the line? Is that expected or?
Mm, That's a good question. Yes, as we are, we are now in a phase that we are creating, publishing the results we are having at this moment. So we first published, we have a first article published that describes the QSEC, and I believe that well, at least our intention is to make all of this publicly available, as we think it is the best way to proceed. We are using all publicly available interfaces. Well, they are our own implementation. It is our own implementation, but we think that yes, that in the near future we will be able to make not only the the controller, the QSEC, but also the virtual KMS and any other entity we develop available. So yes, I would say yes.
Okay, thank you very much. That sounds great. Please present it then in an InfoShare.
Okay.
Any other questions?
Hi everyone, I am Eire Salegi, and I will do the presentation about the KMS framework that my colleagues introduced earlier. The title of the presentation is Basque Open and Standard Compliant KMS for Quantum Safe Network by EHU, and without further delay, I will proceed with the presentation. So the presentation is divided in 4 parts. In the first place, I am going to do a brief introduction. Then I am going to introduce the adaptive security framework along with its implementation. And finally, I am going to introduce some conclusions. So we all know that QKD is the most promising technology against the quantum computing threat. However, it presents some challenges when integrated in real-world networks. So firstly, QKD has a physical constraints as a QKD link cannot exceed the distance of around 100 kilometers. And in addition, it has a point-to-point topology by nature, which real-world networks don't, so that makes it a challenge when integrating it. And nowadays, it is unfeasible to have a fully quantum network due to its cost and technical boundaries. So to address all these challenges, we have developed an adaptive security framework, and here are some of the key features of the project. So the architecture of the framework includes an SDN-based centralized controller that, as my colleagues mentioned earlier, called Quantum Security Controller. This framework supports heterogeneous networks where QKD-enabled nodes and classical nodes coexist. This image shows an example of it, where pink nodes represent the quantum nodes and the blue nodes are the classical nodes. In addition, this framework enables an end-to-end key establishment that adapts to the network's capabilities. And finally, it leverages PQC and QKD hybridization. Regarding the architecture, it comprises 6 different planes, which I'm going to explain one by one. The data plane consists on simply the infrastructure of equipment for user traffic transmission, such as routers or switches or so. QKD modules and links are part of the quantum plane. These QKD systems are responsible for generating keys and forwarding them to the plane above. In fact, the plane above is called Quantum Key Management Plane, and the KMS is located here. This entity, the KMS, is just deployed in the quantum nodes, not the classical nodes, just in the quantum nodes. That, as mentioned earlier, this KMS stores the keys handed by the QKD system below. It also implements the EduQKD 014 standard to deliver these keys to the plane above. In addition, it receives controllers network instructions and implements other functionalities related to the relying keys, including the draft ETSI 020. above the KMS, the framework introduces a new entity named virtual KMS, which abstracts the complexity of the underlying infrastructure from applications. In contrast to the KMS, the virtual KMS, it is deployed in both quantum nodes and classical nodes. In fact, this approach allows classical nodes to establish quantum-safe keys. It also receives requests from the end-user application, leveraging the ETSI QKD 014 standard. And finally, under the instructions of the controller, executes operations related to QKD, PQC, or hybridization to deliver quantum-safe keys. Regarding the famous controller, the control plane consists of the quantum security controller from now on called QSEC. I will refer to the quantum security controller as QSEC. This entity centralizes the network and security management. It maintains a global view of the network topology, as the rest of the architecture is network agnostic. On the other hand, executes path functions. It also introduces a security level assignment function that assigns a security level to each application pair, depending on their quantum capabilities and quantum path, the ones that David mentioned earlier. This will therefore determine the key obtaining procedure. And to conclude, finally, the end user plane is where the key requesting applications are located. These applications request symmetric keys without knowledge of the underlying infrastructure. Regarding the procedure to establish an end-to-end key, it proceeds as follows. So you can follow my explanation on this image over here. The first step is that the initiating application requests a key to its virtual KMS. Then the virtual KMS queries the QSEC controller for the security level of the key requesting application pair. Next, the QSEC assigns a security level, and I will dive into this later on the presentation. Subsequently, the virtual KMS requests a level-specific configuration, and QSEC performs the required installation of assignments on the security management plane or in the quantum key management plane. With the configuration set, virtual KMS starts the corresponding secure key derivation process. That will depend on the assignment security level. Finally, virtual KMS delivers the key container to the initiating application. On the target application side, firstly, the target application will request a key to its virtual KMS, but in this case, specifying the key ID. Then the virtual KMS queries the QSEC for security level, as in the initiating application case. The QSEC assigns, therefore, a security level, and later the virtual KMS will request a level-specific configuration, but the QSEC, as it maintains the state of the configuration, it checks the state of the configuration and responds that the key is ready to be delivered. Finally, the virtual KMS retrieves the key and delivers it to the target application. So this is how the end-to-end key establishment works, basically. Regarding the security assignment, as demonstrated in the end-to-end key establishment process, the security assignment plays a crucial role. During this phase, the QSEC executes the security assignment function that assigns a security level depending on both on the quantum capabilities of the nodes and the quantum path ability of the key requesting nodes. There are 4 possible security levels: level 1, level 2, level 3, and level 4. I'm going to explain them one by one. In the level 1, QSEC will assign the level 1 when both nodes have quantum capabilities and are connected via direct QKD link. In this case, the final key is directly the QKD key retrieved from the KMS of the QKD system. this image represents a level 1 scenario where node E and node F both have quantum capabilities and share the same QKD link. In level 2, both nodes have quantum capabilities, but they don't have a direct QKD link. Therefore, a trusted relay approach must be followed. In this example, nodes D and F don't share a direct quantum link, so node E acts as trusted relay node, relaying the QKD key shared with node D to node F. This relay is protected with one-time path encryption. In level 3 scenario, one of the endpoints has quantum capabilities, whereas the other one does not. In this case, a relay and hybridization approach is followed. In this example, node E relays a QKD key shared with node D to node C. So a QKD key generated via this link is relayed to node C. Between node D and node C, which are the nodes requesting keys, is established a PQC secret key. The final key will be derived using the QKD and the PQC keys as inputs. It is worth to mention that this final key will be secure as long as at least one of the input keys remains secure. Finally, level 4 is applied when both requesting nodes lack quantum capabilities. In this case, a purely PQC-based shared secret is established. In summary, this table shows an overview of the 4 security levels and the nature of the established keys in each level. So regarding the implementation, the 3 main entities of the framework, along with all the involved procedures, were implemented following a modular approach. This modularity provides several advantages. Firstly, it enables independent development, testing, and integration of individual modules. On the other hand, it enhances resilience and maintenance, as faults in one module do not propagate across the entire system. In addition, it allows scalability and extensibility, allowing new capabilities such as additional routing algorithms, routing metrics, or security policies to be integrated seamlessly. Finally, it enhances interoperability, as modules can be reused or replaced to interface with third-party implementations or hardware components. Actually, we recently faced a similar scenario where we had to replace one of the modules of the KMS to interface with a real QKD equipment instead of a QKD simulator. As we saw in the previous picture, each module is responsible for certain functionalities. Regarding the QSEC, security assignment module executes the security assignment function that we described earlier. The path computation module executes path-related functions. Then the virtual KMS module interfaces with virtual KMS, receiving the security level requests and configuring the rules for each level. I am sorry, I just realized that these 2 modules must be intertwined. So here should be the virtual KMS module that communicates with the virtual KMS, and here should be the KMS module that connects with the KMS. So the KMS module interfaces with the KMS instances to configure each security level. Similarly, the main modules of the virtual KMS are the following. A security control module to communicate with the QSEC, Secondly, the KMS connection module that to communicate with KMS instances. In addition, a remote sync module to communicate with other KMS instances. Also, there's a key delivery module to receive key requests from applications using the EduQKD 014. So
Yes.
I was explaining the modules of the virtual KMS as far as I remember. So I mentioned the security control module to communicate with the QSEC, the KMS connection module to communicate with the KMS instances. In addition, a remote sync module to communicate with other virtual KMS instances. Also, there's a key delivery module to receive key requests from applications using the EduQKD 014. And finally, a quantum safe key management module to perform internal operations related to each security level. Regarding the KMS, it has the following modules: a security control module to communicate with the QSEC. Secondly, a key delivery module to communicate with the virtual KMS to deliver the keys. In order to communicate with other KMS instances, we have a local sync module. I had to highlight that this module is to communicate with KMS instances within the trusted node. The remote sync module is responsible for communications with peer KMS that are not within the trusted node, and they are in fact in another node. Finally, there is a key management module to manage the storage and retrieval of QKD keys. So to conclude, we would like to highlight that this framework has been validated in a virtualized testbed. The obtained results and more detailed description of the framework can be found in the link below. In addition, we have also integrated this framework on a multi-site 5G testbed using the framework provided keys to secure different inter-site interfaces of the 5G network. Additionally, this testbed uses commercial QKD equipment from different vendors, demonstrating the interoperability of the framework. Finally, currently the source code, as in advance mentioned Susanne, is not available, the source code of the framework, including the QSEC source code, but we do plan to publish it open source in the future. So thank you all for your attention, and if you have any questions, feel free.
Okay, thank you very much, Eire. And of course, I'm glad to hear that you're planning to also make this open source. This is very exciting work. I see one question in the chat. Can you paste the archive link into the chat? I think you should be also able to see it in the presentation that's available on the events page. But if somebody can paste it in the
I'm on
chat.
it. I will paste it now.
Okay, thank you very much.
Okay.
Are there questions other than the chat question we just had?
So,
I saw that you had these security levels 1, 2, 3, 4, with 1 being the strongest with the all QKD, right? Who decides which level is being chosen? Is this something that an application can request as a quality of service feature, or is this being used as best as available?
the QSEC controller is the one responsible for deciding which is the security level assigned to application, and it just depends on the capabilities of the key requesting nodes. So if both key requesting nodes have quantum capabilities, and a level 1 or level 2 will be assigned. So for example, if the application node doesn't have quantum capabilities, the application cannot request a level 1 or level 2 security level. I don't know if that answered your question.
Yeah, okay, I see what you mean. So it's very much dependent on availability, of course, yeah.
Yeah, it depends on both the quantum capability of the nodes and the quantum path availability. Yes.
Just to add one small thing, I am Anne. I work with Eire in this framework development, and the thing is that the framework is transparent for applications. So they just request a secure key, the securest key possible, and then the QSEC is the one which is responsible of assigning the highest security possible, depending on the as Eire said, on the availability and the capabilities.
Okay. Okay, thank you very much.
Welcome.
Any other question? I have one more. Then you had in some of these images on, I think it was on the very last slide and the one before, you had local and remote sync modules.
Yeah.
How do you sync them, and what precision do you think you need? Because I understood this as precision also syncing also between nodes, not just
But no,
locally.
it's not that synchronization, Susanne. It's just an application level synchronization. I mean, to synchronize the security mechanisms or the
Oh,
cryptographic algorithms, it's not a time synchronization.
okay,
We
okay,
call
okay.
them synchronization, but it's not time synchronization.
Okay, then thanks for clarifying.
It's okay.
Any other question?
Thanks a lot, Susanne, for inviting us. Thanks also for the previous speakers for giving us some very interesting talks. I'll talk a little bit about what SURF has developed and deployed, which is called now EduQKD. And I'll start first with a general overview, and then I'll go a little bit more into detail into the separate packages. So the motivation for this work was we were part of the first phase of EuroQCI projects, specifically the Dutch one, the Nederland one, so QCI NED. And at the beginning of the project, we essentially had made a bit of a survey of what is currently available, what are the options for deployment. And while there were quite some options for hardware, there was, in our opinion, a little bit of a gap for software. So back then, all software that was available to kind of the kind of stack that's necessary for deployment was either proprietary, very lacking in features, or a combination of both. Different vendors, or the hardware that different vendors, also the software that different vendors offered, was not interoperable at all. Of course, QKD has the known range limitation. But also at SURF, we kind of wanted to play around a little bit with a more decentralized approach. So not using a centralized controller, because that kind of, in our opinion, followed a little bit more the development of the classical internet. So we wanted to try out something as well. And so this is how we started our development for EduQKD. So we then developed an open source software stack that is, first of all, open source, of course, because we wanted to really encourage collaboration among the QKD deployments, also potentially between NRENs, but anyone who is interested. It's, of course, ETSI compatible to comply with existing standards. It should be capable of key relaying, key forwarding, key extension, however you want to call it, to make it practical, of course. And importantly, we wanted it to be fully vendor agnostic, so to avoid vendor lock-in. So you can kind of have this little picture that I have here at the bottom, where you have a network that is very heterogeneous, and you move to something that's a bit more to the right, where you can just exchange key. And as I said, we wanted it to be decentralized. So, for example, to also avoid having a single point of failure. And what we ended up with for our deployment, so this is deployed like that also, and this is running on our testbed, is kind of this layered architecture that is also very similar to what we've heard in the talks before. So we are using for automation and orchestration, we are using the existing open source project of the workflow orchestrator. So this has this kind of, it kind of takes human input of what you want to do. For example, you want to deploy a KMS node or something like this, and translates it into workflows that kind of imports different things from different databases and so on, and creates the node then in your service description. This then, in the next layer, we call it the quantum domain control layer, or we have then our first package that we developed, which is the EduQDC, the Edu Quantum Domain Controller, which has the main role to set the configuration of devices and deploy different packages, different nodes and so on. And then on the layer below, the physical layer, we of course have the QKD hardware, so the quantum key modules of different vendors, and then also the key management services or servers, so the KMSs. And so there's specifically as our second package, the EduKMS, as we call it. That then the hardware does the point-to-point key generation, but they can't talk to each other and have other limitations. But then our KMS would then take over key relaying, routing, and all these sort of things. It's also, I'll mention this again later, but it's important here that also these layers are somewhat independent. You can deploy it like this with all these parts, but you don't have to. So the KMS will also work without the QDC or the workflow orchestrator. And also you can just deploy the QDC and the KMS. So it's a little bit mix and match. The APIs are very modularly defined also. So it should be very, very easy to mix and match. Now, we have published the software under an open source Apache 2.0 license. You can find them under this link, or just Google it, or I don't know, if you're under 20, you can probably ask ChatGPT, I don't know. But there's two packages, the KMS and the QDC. So as I said, the KMS, it does implement key relaying and something that we call key flooding or pre-buffering, or however you want to call it. I'll go into detail about this a little bit later. It's fully vendor interoperable. So in our deployment, we have also different vendors. Also, we have MDI, QKD, DV, QKD, and so on. And it operates fully decentralized and independent. So if the domain controller goes down, or if one of the nodes go down, the other ones are still fully operational. And then we have the quantum domain controller, EduQDC, which mainly it's much more simple than what we've heard before from other domain controllers, but that is by design. So it basically just defines the interface towards the workflow orchestrator. Then it can deploy the KMSs and push configuration. But other than that, it doesn't do anything. So for the real operation, you don't need to contact the domain controller every time. And it is, again, it's optional and it's standalone, so you don't need it if you don't want it. Now, so the development, we kind of finished this as part of our deployment of our testbed. So we finished this around June. But the development of both software packages will continue in follow-up projects that we have. So, for example, the SAF call, where we connect within the Benelux countries. We are very interested in finding co-developers to ensure, of course, the sustainability of the project going forward. So if anyone is interested, please reach out. And we're also open to onboarding new developers, of course, in particular, if someone wants to contribute. There's also, for both packages, I believe there's tutorials. They're very simple, but if you want to get your hands dirty, you can do it. So a little word about governance. Currently, for exclusively practical reasons of being able to publish this as soon as possible, it is governed by us, SURF. But if there's any interest in co-developing this software, we are very happy and very open to move to a more open and neutral governance model. So SURF also has a history of doing this. So for example, with EduVPN, for example, via the Commons Conservancy. So this is important to mention. If you want to contribute, we don't want to keep ownership of this or governance of this project necessarily. So how does it work? So here's a little video that we also submitted to the European Commission of how you set this up. So this is the workflow orchestrator. It starts with a little bit of a page where you can put in some information as user input. So for example, IP addresses and so on. And then essentially it walks through a few steps that are necessary to deploy the software. And then it's the software, and then essentially you're done. So it's kind of has this graphical user interface. So it's quite nice, and as I think quite simple also to work with it. And these are basically what you just saw is one of the workflows that we implemented. So specifically the one to deploy the KMS. There's then different ones that we have. So the KMS, then a link between the KMS. The key modules need to be registered in the system as well. You can link them, so the topology of the underlying physical hardware is also known. And then, of course, you also need to create or be able to work with user subscriptions. So this is called what we call the QKD service. So there, you could set things like how much keys a user is allowed to request on links or whatever, these kind of things. If you want to deploy this, then there's a few prerequisites that we've defined. So devices must be installed with minimal config. So they must be reachable remotely over the network, essentially. There should be classical connectivity between your nodes. And then if you like, but you don't have to, you can have the workflow orchestrator deployed. And then you can just use this graphical interface that I just showed previously. And then essentially you deploy the EduQKD on the server. And then you can, so this is a Docker compose. And then from the workflow orchestrator, from this GUI, or directly via the QDC, with executing the necessary commands, it's also fairly simple. You then deploy your network. So you start with the KMSs, you connect them, so it's kind of clear where key can be extracted. Then you can add as many quantum key modules to the KMSs as you like, link them so the physical topology is clear, and then you can add user subscriptions so you know where, on which links your client can request. And then at the end, you end up with something that looks a little bit like this. So the workflow orchestrator kind of sits at the top, orchestrating everything. The domain controller at this point becomes quite passive. So only if you want to modify anything, it will push new config. And then at the layer below, you kind of have the KMSs that are connected to each other. Have a connection with MTLS, so you can use whatever you like there for the key. You could use QKD key or PQC or whatever you want. And below that, then you have the quantum key modules. So it can be also anything from any vendor. The maximum thing that you would have to do is program some sort of adapter between whatever the vendor exposes and ETSI 014 if the vendor doesn't offer that even. But if the vendor offers ETSI 014, then it's just plug and play. There's also limitations of it. So this was kind of a minimal thing that we made for our testbed deployment. It's not rigorously pen tested. The authentication is still not quantum safe. So it's really only does key delivery, symmetric key delivery. The routes are static. The key flooding that I'll talk later about is kind of basic, so that could be improved. There has also been papers, I think, by the TU Eindhoven that looked into this. There's a few things that are still hard-coded, for example, key size to 256 and these sort of things. The telemetry monitoring that we've set up, which is quite nice, it has not been published yet. So this is something that we still want to do. And scalability, it has been deployed on a very small testbed of 5 end nodes. I wouldn't say the scalability has been rigorously tested. Then going to the packages. So the EduQDC, so the quantum domain controller, as I said, it's a very simple package. So I'm not going to go into great detail, or I won't go into more detail actually than I have so far. but I'll go into some more detail about the key management server that we have. So also, like in the talk before, we also highly value modularity. And so here I have a slide where I'm just briefly going into the logical components. So at the center, for logically speaking, we have an event loop for fetch, get, relaying. So they it's connected to an event bus where these events are kind of published and listened to. And this event loop also requests the key from the QKM clients, or so from the QKD modules. And then this key material is then kind of handed over to the key service, which is the entity where also a customer would request the key from through the customer API, and then the key gets persisted, I mean, in memory. So key storage and with some metadata. From an architecture kind of view, it becomes a little bit more boxes. But essentially, this is how this will look. We'll have a node, or secure zone, as we called it here, that contains any number of key modules that is connected by MTLS to the KMS. And there's a few Docker packages that are deployed. So we have RabbitMQ deployed to communicate. Then we have a Redis database that does the key storage and metadata storage, and then we have TLS proxies that kind of handle multi-tenancy, so that the customers don't have to request on the same ports. There's if different customers are interested in what other customers do, there's we try to separate it as much as possible. That's basically it. Next, so key relaying. I hope most people are a little bit aware of what this is, but the idea is that because quantum information can't be copied, there's a range limitation on it given by the attenuation of the fiber. So if you want to bridge long distances, you have to either have a quantum repeater, which we don't have currently, at least not outside the lab, or you have to do something called key relaying or key forwarding or key extension, where essentially you take the key material on one link, and then you use that to encrypt the key material from your second link and to send it forward. And so here we specifically implement this using by splitting our key material into monodirectional initiator and responder keys to avoid race conditions. So essentially, if at two ends people want to do key relaying with each other, then the site that that is requesting this, they would use the initiator key, and if someone else requests the relay key to you, you would use the responder key, and so on. So essentially, from the key modules, they would start to fetch key material from the respective key modules, the KMSs, I mean. And then in the next step, we then get such a scenario where we want to actually do the key relaying. So we see here that kind of the neighboring nodes, A, B, and B and C, they have these, all of their key stores to their neighbors are filled, but there's not enough key between, for example, A and C. So this is where we want to relay key. So A would ask B for initiator keys to C, which are kind of these keys in this bucket here, if you see my mouse. Then B would encrypt the BC initiator key with its BA responder keys. A then decrypts these with the AB responder keys it has to obtain then the BC keys, and then it needs to just relabel them as to AC, and then it essentially has a key, the same key as C has. So we have key material between A and C available now. So in the end, we send a confirmation to make sure that everyone knows that this relabeling or this operation has happened, and then we're good. The second thing that I've mentioned now 2 times, I think, is key flooding or pre-buffering or whatever you want to call it. And I'm not going to go maybe through each and every one of these steps. But the idea is that key relaying can happen in two ways. One is on demand, and one is, as we propose here, by flooding or pre-buffering. What we've seen, if you do it on demand, that means if I want to have key between Alice and node A and node D, and there's node B and C in between, for example, if I do it on demand, then that means at the moment when I request key with D, then all the relaying starts to happen, and then I'll get key A to D. We have seen that this, especially in scenarios where key weights are very low, leads to the session being open very long, which is not so ideal. So we tried to implement here an alternative, which is key flooding, where essentially all the key material gets constantly fetched from the QKMs, and then we just do key relaying to every node all the time, such that basically these end-to-end stores are hopefully always filled. And then as soon as I request a key from A to D, the key is immediately available or immediately refused the request. And so here you just see this, how this is stepwise done, but this is just an iteration of the algorithm that I've explained on the previous slides. Basically, you're doing constantly this key relaying. And so this has obvious advantages, but also obvious downsides, of course, in terms of scalability. Then one thing that is relevant for our cross-border deployments is one thing that we're thinking of currently is if you want to go cross-domain, then of course, ideally, you would want to have maybe a hardware backbone to do this. But what we can do with, or what we are going to do with our KMS is we're going to do a software backbone. So just on top of kind of your national, in this case, the domains are different national networks that have the physical layer and then the KMS layer on top. And so here we propose that you can just put another KMS layer on top as a software KMS backbone that can then interface with the underlying national KMSs and do these cross-domain connections. And this brings me, I think, almost to the end. So the development roadmap, ETSI 020 integration, we're not part of ETSI, so we're not officially allowed to see the draft until it's published, I hope, next year. So we couldn't integrate this yet, but we would like to. We're going to implement this cross-domain software backbone and test it. We want to publish our monitoring and telemetry code because I think it's quite useful to have. And we want to have a rigorous security audit of our software. And I believe that is it from my side.